Okay, let's continue. If we like to get better solutions, and first I'm going to introduce the okay. This one is the a different numerical integration method. The name of this method is the Gaussian-Quadrature method. And if we like to get the better solution for the numerical integrations, for the trapezoidal rule, we use the 2 data points. In a subdomain. And also for the Simpson's rule, we use 3 or more. And for the trapezoidal rule, we use 2 data points for each subdomain. And the 2 data points, they always occupy the 2 endpoints of the subdomain. If we use the Simpson's rule, then we need to use 3 or more data points in a subdomain. And for these 2 methods, if we use the n data points, then okay. So for these 2 methods, if we use n data points, then for all n-1 degree polynomial functions can be exactly integrated. And not only for all the n-1, for all the lower degree polynomial functions like the n-2, n-3 until the 1st degree, 0th degree, we can get the exact solutions. So if we use the trapezoidal rule, we use 2 data points, then it means for all the linear functions, for all the 1st degree polynomial functions, they can be exactly integrated for the trapezoidal rule. And the Gaussian quadrature method, for this method, it tries to use less data points, but we can get higher accuracy for the results. For this method, okay, we try to use n data points, but we like to get better results compared to these 2 traditional methods. And for the Gaussian quadrature, if we use 2 n data points, then it tries to okay. For the Gaussian quadrature methods, if we use the n data points, we try to exactly integrate for all the 2n minus 1th degree polynomial functions, we like to get the exact solutions. Okay, it's time you can make a screenshot. Okay, and how can we get a better result by the Gaussian quadrature method? And the Gaussian quadrature method, if we use n data points, however, we like to get all the 2n minus 1th degree polynomial functions. For all these functions, we can get the exact solutions. If we use n data points, we will use the okay. We still use the data points to establish approximate functions, and all the solution procedure to establish the g of x, which is very similar to the previous traditional methods, and we use the interpolation function. And this method is the interpolation. Also, it is the Lagrange. Okay, actually, we use a similar procedure to establish the interpolation function g of x, and the interpolation functions, which is also a polynomial function. Okay, also the g of x is a polynomial function, and these procedures they are exactly the same as the Simpson's rule or trapezoidal rule. The only difference between the Gaussian quadrature method and the Simpson's rule or the trapezoidal rule, the only difference will be the locations of the integration points. Okay, the difference between the Gaussian quadrature method and the Simpson's rule or trapezoidal rule will be we will use different locations for the data points. For the Simpson's rule or trapezoidal rule, the data points will always located at the end points and equally divided internal positions for the data points. Therefore, if we use the trapezoidal rule, the two data points will be the two endpoints. If we use the 3-point or the second degree Simpson's rule, the 3 data points will be 2 endpoints plus 1 middle point. Okay, the middle points and the 2 endpoints will divide the subdomain into 2 equally divided area. Okay, but if we use the Gaussian quadrature method, although we use sometimes we have the 2-point Gaussian quadrature rule and the 3-point Gaussian quadrature rule. If we use the 2-point Gaussian quadrature rule, the 2 data points, they will not be the endpoints. They will not be the endpoints. Okay, and the next thing I need to introduce, which is the Legendre polynomial functions. Okay, first you need to understand what are the Legendre polynomial functions. Then you can understand why the Gaussian quadrature method can use the same number of the data points, but for this method you can get better results. The Legendre polynomial functions, which is a series of functions. Okay, so a series of functions means there are infinity the number of the Legendre polynomial functions. It includes the 0th degree Legendre polynomial function, the 1st degree, the 2nd degree. For all the integer number of the polynomial functions, you can find the corresponding Legendre polynomial functions. So so it is the P0 of x, P1 of x, P2 of x, and you can get infinite number of the Legendre polynomial functions. So that's why we say it is a series of functions. It is not only a single function. You can find a series of the functions. And the second character of the Legendre polynomial functions, it is defined okay. The Legendre polynomial functions will always defined at the range from the -1 to +1. You cannot use the Legendre polynomial functions other than this domain. For the Legendre polynomial functions, the domain will always be the -1 to the +1. The reason why the range is fixed at I think one of the reasons is the Legendre polynomial functions, they are derived from the either cosine function or sine functions. And if you check the values of the sine functions, it is a wave shape of the function values. And the minimum value will be the -1. And the maximum value of the sine functions, which is equal to 1. Also, for the cosine function, the minimum is equal to the -1. The maximum value is equal to the +1. The function values, which varies from -1 to +1. The Legendre polynomial functions, they are derived from these two functions. So, if you like to use the Legendre polynomial functions, they should be always be the -1 to the positive 1. The range should be fixed. And also, it has characters. Okay, if we multiply two different Legendre polynomial functions, since the Legendre polynomial functions, they are a series of functions. The I and the j, they could change from the 0 to the infinity integer numbers. If the I is not equal to j, if we multiply the pi of x by the pj of x, and also if we integrate the multiple of these two functions from the -1 to +1, it will be equal to 0 if I is not equal to j. And if the I is equal to j, then okay, so that's one important character you need to remember. For different Legendre polynomial functions, you can get different results. Okay, take a screenshot, then I will erase. You can check the Wikipedia by yourself. Then you can get the Legendre polynomial functions. And that's what I did before this hour. I checked it from the website. Okay, I just list the first four Legendre polynomial functions. Okay, so but if you check the table, you can write a lot of Legendre polynomial functions. So it is a series of the polynomial functions, and let's use some real example to check the characters. So if we integrate then it will be the okay. So the P0 times P1, if we integrate them from -1 to +1, you can find the results equal to 0. But if we integrate okay, so if we multiply the P1 by the P1 in the range from the -1 to +1, the integration of P1 times P1, the results, it is not equal to 0. But for all different I and the j, if we multiply these two together, and the integration will always be equal to 0. And also you can prove Okay. If the h of x, which is an nth degree polynomial functions, then the h of x can always okay. It means we can always use the Legendre polynomial functions to express all the nth degree polynomial functions. It is a linear combination of the Legendre polynomial functions. You can always get the results like this one. Okay, a linear combination of the Legendre polynomial functions can express or okay. Also, we can use the linear combination of the Legendre polynomial functions to express all the nth degree polynomial functions. Okay, and probably we can do you can take a screenshot. Then I will keep the upper half of the blackboard. Okay, let's try. Okay, it is an arbitrary polynomial functions, and how can we express these functions by the linear combinations of the p0, p1, and the p2, and the 3x squared. Okay, so remember only the p2 of x will have the contributions to the x squared, and the p1 of x and the p0 of x will contribute. For the p1 of x, it will contribute only to the first degree of the x, and the p0 will contribute only to the constant of the constant term of this one. So we know the alpha 2 is equal to 2. Okay, then. Okay, the only term which will contribute to the x raised to 1 will be the alpha 1 times p1. So we know the alpha 1 is equal to the -1. And the constant okay, so we can get the okay, after you solve all the coefficients, then you can say Okay, you can do this for all the nth degree polynomial functions. Then you can find no matter which, no matter the what are the coefficients for the h of x, you can always solve the coefficients for the linear combinations. Okay, we can do this for all the nth degree polynomial functions. Okay, take the screenshot. Okay, let's try to solve the problem. Okay, and remember, for the Gaussian quadrature method, the domain of the integrations will always it is always integrated from -1 to +1, and assume the is okay, it is an assumption. The f of x is 2n-1th degree polynomial functions. And right now we try to integrate this problem. And we will use okay, since we know the function of the f of x, so if we take n data points, then we can calculate the corresponding function values f1, f2 until the fn. If we take n data points, then we can use the to establish the g of x, which is the okay, so the f1 times L1 of x plus f2 times L2 of x, and the L1 of x, which is the Lagrange interpolation functions. Okay, this one is the Lagrange interpolation functions. Also, you can write the other n-1 L functions. Okay, so that's the approximate functions g of x. The g of x it is derived from the n data points. Okay, you can take the. And we can define error functions. Okay, since the f of x, which is a 2n-1 degree polynomial functions, and the g of x, which is g of n minus 1, it is okay, so the g of x is an n minus 1th degree polynomial function, and the f of x, which is a 2n minus 1th degree polynomial function. So it is not possible to be these two functions, they are same, since the degree of these two functions, they are different. The f of x, which is a higher degree, and the g of x, which is a lower degree polynomial functions. So this one is a 2n minus 1, and this one is n minus 1, and for this one is a 2n minus 1. So if we define the error functions, the error functions will be 2n minus 1 degree polynomial functions. Which one is the so-called error function? And but we know the e of x1. Okay, but although these two functions, they are different, but we know the g of x is established from the n data points, so we can guarantee at all the for all these n data points, we can get zero value of the error functions. Okay, take the print. Okay, so by the definition of the error functions, the integration of the f will be equal to the integration of the g of x plus the integration of the error functions. And when the Gaussian quadrature, when he derived this method, he thinks if we can make the integration of the error function is always equal to 0, then the g of x will be the exact solution of the f of x. Okay, and if the integration of the error functions is always equal to 0, then the integration of the f of x will be always equal to the integration of the g of x. But how can we guarantee the integration of the e of x always equal to 0? And remember, we have n solutions. Okay, we know there are n solutions, so we can know the E of x and we know the E of x, which is 2n minus 1, and for all these terms. Okay, since we know the error functions must be 2n minus 1th degree polynomial functions, and also we know there are n solutions for E of x equal to 0, then we can use the x minus x1, x minus x2 until x minus xn multiplied by another n minus 1th degree polynomial functions. And since we know we can use the Legendre polynomial functions to express the h of x. So the h of x can be expressed by okay, so the h of x can always be expressed like this one. And then how can we get the integration of the error functions, which is always equal to 0? The only possibility is the first n terms multiplied together. If this term, which is equal to Pn of x, okay. Since we have not decided where are the data points, so the x1, x2, and until the xn, they are still arbitrary numbers. So if we can control all these x1, x2 until xn, they are the solutions of this one. So okay, so if we can control the x1, x2 until xn, they are the solutions of the Pn of x equal to 0. Then we can control if we multiply all these together, then we can get the Pn of x, or you can say which is the beta times beta Pn. Okay, take a screenshot, then I will continue. Okay, so then let's take n equal to 2 as an example. Okay, then P2 of x is equal to 100. Okay, if we solve the P2 of x equal to 0, then you will find the two solutions of the x1 and the x2. They are the negative of square root of 1/3 and the positive square root of 1/3. And okay, so if we use the x1 and the x2, and for this x, they are the solutions of the p2 of x equal to zeros. Then if we multiply these two terms together, you will get a constant, right now the constant, which is the 3 seconds, and multiplied by the p2 of x. Okay, so first we need to find these two. And the g of x equal to f1 times L1 of x plus f2 times L2 of x. Okay, you will find the two Lagrange interpolation functions. They are not related to the f of x. The L1 and the L2, they are related only to the locations. They are related to only the locations of the data points. So they are related to the negative square root of 1/3 and the positive square root of 1/3. But they are not related what the function f of x you are calculating right now. And what is the L1 of x? Okay, that's the L1 and the L2. If we use the Gaussian quadrature to solve the problems, we will integrate the approximate function g of x. And the g of x, which is established from the two data points, and right now the two data points, they are located at these 2 points. And we need to calculate the f1 and the f2. And the f1 and the f2, they are related to the given function of f of x. Okay, you will find that the f1 and the f2, they are the calculated values, and they are not related to the x. So it will be the okay. Remember, we know the L1 and the L2. So the integration of the L1 and the L2, they can always be calculated since we know both x1 and x2. And if you check the integrations, you will find this one is equal to 1, this one is equal to 1. So this one will be the f1 times 1 plus f2 times 1 equal to summation f of xi times wi. And for the Gaussian quadrature method, if you decided the number of the integration points, then the locations of the data points, they are fixed. The data points, they are always the solutions of the nth degree Legendre polynomial functions. And if you decided the number of the n, the weight of each data points, they are also fixed. So that's why you can use a table the result. Usually you can use the search on the website, or you can use the Wikipedia. It is very easy to find the locations of the data points and the weight of each data point. And the calculations of the numerical integrations, they are relatively easy. We just need to calculate the function values at the integration points, and then multiply by the corresponding weight of this point. Then sum up, then you can get the results. Okay, I think that's the end of this course.